This is just too damn hilarious. Alright, so I just put some little dots there for the zero markers. Okay, so that's the A trace showing the battery voltage, common drain, common MOSFET drains on the board here, right? There's my color-coded cables going over to no MOSFETs. I don't have any MOSFETs plugged in. I've discovered that this circuit makes an excellent sort of kind of MOSFET tester. I got everything else wired up just as usual. As is in, to be clear, this is the circuit that I'm using right here, except I'm using the scope to monitor the MOSFET common drains from this point with respect to ground, and I have a 36-volt battery pack in there. Okay. Other than that, okay, I'm monitoring the gate, or rather the gate drive signal on one channel of the oscilloscope and the MOSFET common drain on the other channel of the oscilloscope. Okay, other than that, this is the circuit. Alright, this is the circuit I'm using. Q2 times 4 over here. Q1 single MOSFET over there. Or that's where they would be if they were plugged in, but they're not. Okay, there's my gang of 4. There's my known bad 5th MOSFET right there. Okay, this one is partially open, or rather partially shorted, I should say. Okay, so but these are all good, but I don't have any of them hooked up right now. Okay, so I just want to show you that here I've got the battery connected. All right, function generator idling, set to produce negative going pulse, and I'm going to turn up we're at 5 volts per division as usual on that one, and 20 volts per division on the common MOSFET drain trace. Okay, so I'm going to turn up the amplitude to give us a good negative going 5 volts, and you see nothing happens there. I'll turn it up a little bit more, and nothing happens because there's no MOSFETs. So I'll use the offset knob to raise that signal up and lower it down. Nothing. Okay, no offset now. All right, now what I'm going to do is just take one of the, I've shown you that the leads are color-coded and they're labeled to the common bus in there, so everything ought to be cool. So I'm going to take one of the Q2 leads, the one marked number 4 over here, gain, drain, source, and it was right there, gain, drain, source, gate, drain, source, right? Okay, and I'm going to just plug it in, plug one of the MOSFETs in, alright, one of the known good ones first. Let's just plug that in, like that. I don't have a lot of hands. Oh, look, oscillations already. Oh, I meant to do that with function generator drive turned down. Okay, so let me do that again. Let me unplug that. Okay, and what I'm going to do is just kind of touch it in there briefly like this for a minute, on and off. Okay, if I can manage that. Okay, so watch the function generator trace. Okay, boom, boom, on, off, on, in, out, in, out. There's no change in the function generator trace, right? So now I'm going to go ahead and plug it in hard. Baby, don't you love it when I talk dirty? If I can find a hole. Alright. There we go. Okay, now it's plugged up properly. And no other MOSFETs are in there. No, none at all. Okay, so now we're going to turn up the amplitude, and there's our nice oscillations. So let's note some features here. There's some fuzz on the bottom part of that, on the most negative part of that bottom going pulse, and the oscillations on the common MOSFET drain are there, really nice. And if I bother to go ahead and use the delayed time base, might be able to catch just the very start of one of those oscillations, possibly. There we go. Okay, so you can see that the oscillations have the same form, that slow onset and all of that, as the ones that Ainsley has shown in the paper. So we're looking at the Ainsley oscillations here. There's no doubt about it. All right, we go back to the normal time base. Okay, now that's just with one Q2 MOSFET in the circuit, no other MOSFETs. Okay. Okay, now I'm going to turn this back down, so we're idling again. Sorry, the camera is an autofocus camera, and if it doesn't see anything coherent, it tends to try to go out, in and out of focus. So anyway, now we're back to idling. Drain trace is showing battery voltage. So I'm going to go ahead and unplug that known good MOSFET, and I'm going to take the known bad MOSFET over here, and I'm going to do the same thing. Okay, I'm just going to plug it in briefly. If I can get my hands on there, like this, and then unplug it. Okay, so watch the signal generator trace when I do that. Okay, you see that? That's plugged in, that's not plugged in. Plugged in, plugged out. Remember how the other one, the good one, behaved? There was no change there. So this is showing that this MOSFET is shorted internally. It's drawing down the function generator. Now I'm going to go ahead and plug it up hard, like that. So now that's a known bad MOSFET. Okay, now I'm going to turn the amplitude up again to get our nice negative going pulse. Looky there. We got this oscillations. Okay, except there's a little bit, the difference is that I have to get a little bit more amplitude going on the function generator, and there's a little bit more fuzz in the most negative part of the downward going pulse. Okay, now let's see, again using the delayed trigger time base, let's see if we can resolve those guys. Let me get a little bit better focus here. And there you go. Okay. So the only difference I can see is that the onset is a little bit more delayed. Have I got it on 1 microsecond? Yeah, I do. Okay, so the onset of those oscillations is a bit more delayed, and there's a bit more fuzz on the gain or the gate trace, right? But they're the same oscillations, even with a bad MOSFET. Isn't that something? All right. So this circuit makes a pretty good MOSFET checker, and clearly it makes no difference whether there's with the negative going pulse, makes no difference whether there's a Q1 MOSFET in there or not. Right? I can put one in. Let's go ahead and put in one of these good ones over here. Okay. And so now what happened? All right. Now, if we have a negative going pulse, get those massive oscillations, and if we use the offset control to raise the pulse positive, we see the Q1 MOSFET switching on now, right? Here, if we go so we know those oscillations are coming from the Q2 MOSFET, right? I mean, I think we just proved that, right? If I unplug the Q2 MOSFET and then do, oh, looky there, got oscillations now too. Okay, so either, oh no, yeah, that's right. So I got no Q2 MOSFET in there, just a Q1 MOSFET. All right. So it looks like, oh, wait a minute, but that's the bad MOSFET. Let's put a good MOSFET in there. See what happens. All right, now we got a good MOSFET in there. Oh my God, even more massive oscillations from just a Q2 MOSFET. And if I plug a Q1 MOSFET in, yeah, here we go. Here's the Q1 lead. So a Q, see how confusing this all gets? So if I plug a MOSFET into the Q1 slot, boom, now the oscillations have gone away, and then if I use offset to go up, we see the Q1 MOSFET switching on, and if I go down sufficiently, the oscillations come on strongly down there. Now, are those coming from the Q2 MOSFETs? So let's see. Let's just pull. This is so confusing. Q1, Q2. So this was the one I had hooked up as a Q2. We'll pull that. And now, let's look at the, if I vary the offset, that's Q1, must be because it's the only MOSFET in there, and no oscillations down there. Okay, so welcome to the garden of uninterpretable results from the Rosemary Ainsley MOSFET stress test. Thanks for watching. Oh, wait a minute. So let's just plug this single Q2 MOSFET back in like that. Alright, so this MOSFET is a Q2 MOSFET, and the one that's marked 5 is always the Q1 MOSFET because it has a different plug on the end, right? So that's how you can tell. So now we have a Q1 and a Q2 in there, and if I go negative on the pulse, you get oscillations. If I go positive on the pulse, you get a transistor turning on. All right. And notice that the oscillations are in the anti-phase from where the transistor turns on. Right? I'm just moving the offset control up and down here, up and down. All right. Okay. Oh, wait. Let's leave it like this. Oscillations. Okay. Thanks for watching.